Okay, we've been discussing we've been discussing oscillation, simple harmonic motion, and now in topic 4, we will be looking at wave characteristics. So we're also going to study waves and special characteristics which are unique to waves, as well as some other things about waves. We'll learn it when we learn it, right? Okay, a mechanical wave is the propagation or the passing along of a disturbance through a physical medium. And the disturbance is being passed through the physical medium, and the disturbance is some disturbance in the physical medium which is passed along. So what does it mean? This is a little ambiguous. What does it mean that a disturbance is propagated through a medium, is carried through the medium, or passed along through? Well, think of a medium as a web of interlocked but movable particles, right? That's what we mean by physical medium. If you displace one particle upward, for example, push it upward, then the adjoined particles will get pulled along upward with it. Right? So if you let go, then the particles will return back to equilibrium. Kind of like if you have a what's a good example? Let's say you have like a long sheet, right? Just a bed sheet, and each corner is being held by a person, and people are holding this bed sheet kind of taut so that it makes a flat surface. So they're all holding a corner, holding it taut, and it's making this flat surface. If you press up at one point in the middle of the bed sheet, right? Just pushing on one point, because those bed sheet particles, because they're connected, pushing up on the one point causes adjoined or nearby, neighboring bed sheet particles to also move up a little bit. They may not move as high, but they do move up a little bit. They make some sort of angle. Right? A web of interlocked but movable particles. That's all a physical medium is. Right? So when we say that a disturbance is propagated, we mean that the displacing force, right, or the displacement is going to be passed along through the medium. So the thing that pushes particles up in a wave is getting passed forward. That force is getting passed forward through the medium so that successive particles are raised and then lowered and then returned to their original position. Okay? So the disturbance is being propagated, the force is being propagated, and so is the displacement that the particles experience. Now, because of that, the associated kinetic energy, potential energy, those are also passed along or propagated through the medium. Reflection. This is something that all waves do. They reflect. Right? If a wave hits a wall or another boundary, then it reflects back. Refraction is something else that all waves do. It's another attribute of waves. And it's the change in direction of a wave when a wave meets a new transmission medium. Transmission medium is just another fancy way of saying a physical medium. It's the same as this medium here and this medium. Physical medium is the exact same thing as a transmission medium. It's the physical medium through which the wave is transmitted or propagated. So, for example, if you have sound bouncing, So let's say some sound wave is traveling through the air, and then it hits water, like the surface of a lake. Right? Passing from the air into the water is an example of meeting a new transmission medium. So when that happens, when it meets this new transmission medium, there's a change in direction of the sound wave. And this is true for any wave and any pair of transmission media. An example, oh, look at it, there it is. Not only is this an example when sound passes from air into water, but we could see the same thing if light were to pass from air into water. The light changes direction. Right? So this is true, this actually happens. And this is the reason why when you put a straw into a glass of water, it looks like the straw is broken. Right? The straw continues in the water. It looks like the part of the straw in the water, that part appears to be disconnected from the part of the straw sticking out of the water. And it's because refraction is changing the direction of the light, so it appears different to us. When two waves cross each other, and this is another property of waves, another characteristic, when two waves cross each other, they add together or interfere. Right? This can produce an extra big wave, a really, really big wave with a huge displacement, or it can create smaller waves because those displacements can cancel out. I think this is the final characteristic we'll look at, diffraction. It's the spreading out of a wave when it meets an obstacle or a small opening. And we're going to look at that closer in more detail. And in fact, all of these things we're going to learn in more detail in, not topic 9, change that to option A, which is the first option we're going to study. This is just a brief introduction to waves. The important thing to know for this topic is that all waves have reflection. They all exhibit reflection, refraction, interference, and diffraction. And anything that has these properties could be called a wave. The other thing I want to mention, for all given physical media, for a given physical medium, right, like water or air, for any single physical medium, every mechanical wave in that medium travels at the same speed. So all sound waves traveling through air have the same speed, assuming that the air is all the same. All sound waves traveling through a particular lake, right, they all have the same speed. There are two types of mechanical waves we are going to consider and study: transverse waves and longitudinal waves. We're going to model transverse waves as waves on a string. That's our analogy, you might say. That's our model. And that's what we're going to refer to when we talk about transverse waves. And we're going to model longitudinal waves as waves on a spring. So the spring is our analogy or our model. It's another way of thinking of a model. The transverse wave, the ideal transverse wave, quote-unquote ideal, like the example or the exemplary transverse wave, will be the string, and the exemplary or ideal longitudinal wave will be a spring. Transverse waves are those where the particles of the medium are displaced perpendicular to the direction of the wave. Right? So the particles travel in the perpendicular direction that the wave is traveling in. In other words, if the wave is traveling from left to right, the particles move up and down. Right? You can think of a transverse wave as an up and down wave, and this is clear if you hold a string and you send a wave along the string by snapping one end up and then putting it back to its original position. Right? Sending a pulse down that string. Clearly, the string is not itself moving left or right, so none of the individual particles could be moving left or right. The wave certainly moves from the left to the right, but the individual particles are only moving up and down. A longitudinal wave is one where the particles of the medium are displaced parallel to the direction the wave is traveling in. So you can think of that as a left to right wave on a horizontal spring or slinky. So if you have a slinky stretched out and it's horizontal, so it's parallel to the floor, being held above the floor, if you were to scrunch up one end of the slinky, right, grab your hand forward and scrunch up the slinky at one end and then let go, that compression would travel through the slinky. And in that case, the particles of the slinky are moving left to right. Mechanical waves can be a single pulse, or they could be continuous. And what I want you to do in your notes right now is draw a transverse wave, which is a pulse, and make it consist of just a positive displacement, nothing else. So transverse wave pulse with a positive displacement. Then I want you to draw a longitudinal wave pulse consisting of a compression. Then draw a continuous transverse wave and a continuous longitudinal wave. So the continuous transverse wave will have a positive displacement, positive followed by a negative displacement, and it continues in that fashion. The continuous longitudinal wave will have a positive, let's say positive density, right? A density maximum, so a compression, followed by a density minimum, which is a stretched out region. We call that a rarefaction. So it'll be really, really compressed and then kind of stretched out, and really, really compressed and then kind of stretched out. Right? So draw those 4 scenarios into your notes. Those 4 wave types. All waves travel with a speed, which is called the wave speed, and we simply calculate this or derive the wave speed using distance over time. But here's the technical definition for wave speed. This is the definition for wave speed. The wave speed is the distance traveled by the wave profile per unit of time. So the profile is just the shape of the wave, right? That shape, like the sine shape, that shape is the profile, and that profile moves forward, kind of like the profile of a person, right? The side of their face will move forward. The profile of the wave, the shape, the sine shape, moves forward. Waves are reflected when they meet a boundary, right? We've seen that. When we use our wave on a string model, which is modeling transverse waves, imagine that the 2 ends of the string, right? Let's come up with an example where we imagine that those 2 ends of the string are held in place. We call those fixed ends. And whenever a wave hits a fixed end, it is reflected and inverted. So if you send a positive pulse, right, a positive pulse down the wave, down the string rather, when it hits that boundary, that fixed end, it'll come back, it'll be reflected, but it'll be reflected as a negative displacement pulse, and it'll go back down the string. We're going to look at a simulation which deals with this in class. Imagine that instead of being fixed, let's say that the string is loose at one end, right, like the end of a whip. This is called a free end or a free boundary. Another way, besides using a whip example, another way that we model a free end, besides a whip, is imagine that you tie the end of a string into a loop. So you make a loop with it. Then you place that loop around a pole that is a vertical pole, right? So we've got this pole, and there's a string, and there's a loop, and you've all seen this, you saw this last year. That loop and that end of the string can move up and down the pole. So when a wave reaches this free end, it's free because it can move up and down. It's not fixed, it's not held in place. When a wave reaches a free end, like this, it's reflected but not inverted. So we've been modeling fixed and free ends using our string, which means that we've been discussing these 2 concepts, fixed ends and free ends. We've been discussing them for string waves, which are transverse waves, excuse me. But everything we've said also applies to longitudinal waves. If 2 pulses are sent along a string toward each other from opposing ends, they will cross each other in the middle, right, in the middle of the string. And when this happens, the displacements, not the amplitudes, but the displacements of the 2 transverse pulses add together. Now they add as displacements, and displacement can be positive or negative. So if both pulses, excuse me, getting excited. If both pulses have positive displacements, or if both pulses have negative displacements, then we will have constructive interference, which simply means a larger wave will form. So if you have a positive displacement and a positive displacement, then when these 2 positive humps meet in the middle, they will add together to make a giant granddaddy wave. And likewise, if they have negative displacements, when they come together, they make a giant negative wave. if one transverse pulse has a positive displacement on